Finally, we have come to the end of this course, and we now understand that even an ordinary metal wire can have a significant impact on our circuit, especially on boards that operate at high frequencies. This is because waves reflect and form standing waves on the line, giving the transmission line the ability to convert impedance. This is known as the transmission line effect. Since lines can affect the characteristics of the circuit, they are considered elements that need to be taken into account in high-frequency circuits. As a result, they can no longer be treated as ideal wires. It's worth noting that the transmission line effect is not always a bad thing. Engineers have taken advantage of transmission lines and cleverly used them to design filters and other functional components, even replacing inductors or capacitors. For instance, we can deliberately use impedance discontinuities and control the line length to reflect signals at certain frequencies and prevent them from reaching the load. This is filtering. When a single discontinuity does not achieve the goal, engineers can use more line sections to achieve the desired filtering effect. Examples are the multi-section transformer and stepped impedance filter seen here. Given that transmission lines can change impedance, we can also use them to perform impedance matching. In doing so, we aim to minimize reflections at certain frequencies so that the power can reach the load as efficiently as possible. Designing a matching network is similar to designing a filter, as the principles behind both are the same. Now, you may be wondering why there are single-section and multi-section designs. The answer is simple. For a single-section line, the frequency response curve of its refraction coefficient is fixed. Adjusting the line length only changes the operating frequency, which moves the response from side to side. There is almost no way to adjust its response curve, for example, if we want to control the bandwidth. To overcome this limitation, we can add more terms after the refraction coefficient. This is equivalent to adding more sections to the circuit, which creates additional reflections. There is no great principle in this equation itself. It's just a polynomial that approximates a certain curve. If we could make theta n an integer multiple, this equation would become a Fourier series. However, we use it to synthesize a curve in the frequency domain rather than in the time domain. In this case, we see a periodic, repetitive feature in the actual circuit, such as the step impedance filter seen earlier as an example. Now, when we need to create a larger bandwidth for the circuit, we can add more sections to synthesize a wider frequency response because one section cannot do it. Conversely, we can add more sections to create a narrower frequency response when we need a narrower bandwidth. Additionally, we can use more sections to achieve steeper curves that help us better control the filtering ability at the edges. During the design phase, engineers are primarily concerned with the refraction coefficient gamma, as its frequency response is our design target. By cleverly using mathematics, we can create the curves of gamma's frequency response. Then we must translate them into practical circuit parameters such as line impedance and length so that they can be implemented into the circuit. But the use of transmission lines doesn't stop here. We can also take advantage of the coupling properties between lines to create a filtering effect. In the field of microwave engineering, we frequently encounter three-port networks like power dividers and four-port networks like various couplers. These networks have unique shapes or patterns, and they are not simply metal lines. Their characteristic impedance or line width they are designed to have, together with their line length, give them specific functions. This is why it's crucial to have a solid understanding of transmission line theory. Without it, we can't advance in the world of microwave engineering. This course has revealed the secrets and tricks to help you get your foot into the door of microwave engineering. Maybe in your next circuit design, you'll start using line patterns to create the features you want. Okay, we hope this course has been helpful to you. And thank you for joining us, and we look forward to seeing you again.